Greetings, everyone. I believe you are all well. Welcome to my YouTube channel for Kangaroo Maths and Science Academy. Ladies and gentlemen, today I want to take you through Doppler's effect, where I want to talk about Doppler's effects and its application. This is a grade 12 topic, and I believe you will enjoy. Kindly don't forget to like, share, and subscribe, and also hit the bell notification for future videos. All right, without wasting time, let me share my slides. Now, as I said that this is Kangaroo Maths and Science Academy, where I'll be taking you through Doppler's effect. This is physical science paper 1 topic. All right, without wasting time, let us check what is it that we need to cover at the end of this session. All right, at the end of the session, one must be able to understand or to actually define the term Doppler's effect. And also you should be able to know the relationship between the wavelength and the frequency, particularly when we are dealing with sounds and also light. Right, and again, you must be able to differentiate between the frequency of the listener, I apologize. Differentiate between the frequency of the listener and the source when the source is approaching the listener or when it is moving away from the listener. So it means now we're going to compare the difference between the frequency observed or the frequency heard by the listener and also the frequency produced by the source. So we'll be talking about this. And again, this will take us through the Doppler's equation, and we're going to use this Doppler's equation in calculations. And also we need to know the application of Doppler's effect, particularly in medicine. And this is our exam typical equations, and also in the law enforcement. So we'll be talking about this. And again, lastly, we will have to look at the difference between the red shift and the blue shift when you're talking about light. So this is what we're going to talk about under Doppler's effect. I believe you will enjoy the session, and without wasting any time, let me now take you through each and every step that I just said now. Right now, in terms of Doppler's effect, like number 1, you must be able to define what is Doppler's effect. So now what I will do is I'll just take you through the examination guideline as to what is expected for a learner when he's preparing for his or her final examination in physical science. Paper 1. Number 1, when you are dealing with Doppler's effect, particularly in sounds and ultrasounds, we need to also talk about, or actually one must be able to state Doppler's effect, which is the change in frequency or the pitch. The change in frequency or the pitch of sound detected by the listener. The change in frequency or the pitch of sound detected by the listener, because the sound source and the listener have different velocities relative to the medium of sound propagation. So this is actually defining the term Doppler's effect. So it means in Doppler's effect, we are actually looking at the change in frequency of sound that is detected by the listener, because the sound source and the listener have different velocities relative to the medium of sound propagation. So this is very, 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 very important. Okay, just a minute, guys. Okay, guys, I apologize. Okay, right. Then now, guys, without wasting time, as I was talking about the Doppler's effect, and it means now we'll be talking about the change in frequency between the listener and the source or the producer of sound. So now it means in this section, you must be able to differentiate between the source and the listener. So in other part, the listener is also called a detector. So is the one a detector? Okay, I apologize. So it's the listener or a detector. So it's the one that is recording the sound, the one that is recording the sound, the detector or the listener. Then the source, it is the one that is producing the sound. In other books, they call it a producer. So now we want to look at the relationship between the frequency of the source and the frequency of the listener when the source is moving towards or it's approaching the listener, and also when it is moving away. It can be either the source or the listener. So we are going to look at the change in frequency, the apparent change in frequency of sounds detected by the listener, because the sound source and the listener have different velocities relative to the medium of sound propagation. So that is that apparent change in frequency or the pitch. It's called the Doppler's effect. So we'll be using the wave pitch and the wave frequency interchangeably. So what does this mean? It means the pitch of sound is actually directly proportional to the frequency of sound. So what does this mean? It means the higher the pitch of sound, the higher the pitch of sound, the higher the frequency, the higher the frequency. So they are directly proportional. The higher the frequency of sound. So you need to be able to know that when you talk about the pitch of sound, it's related to the frequency. So the higher the frequency, the higher the pitch of sound. So it's very important to be able to know the relationship between the pitch and the frequency of sound. And again, you need to be able to explain, you actually using appropriate instructions, illustrations, the change in pitch, like I said, the change in pitch observed when source moves towards or away from the listener. So this is what we'll be talking about when the source is moving towards the listener and also when it's moving away from the listener. That change in frequency or that change in pitch, it's what we want to talk about, which is actually regarded as the Doppler's effect. Then again, we are going to solve problems using Doppler's effect equation. And this equation, guys, is very, very important. You need to be able to know it, especially when the source or the listener are moving. Either we are dealing with towards or when we are moving away. Then again, you must be able to understand or to state the application of Doppler's effect, particularly number one in medicine. We'll be talking about this in medicine, and secondly, in the law enforcement. So these are the things that you need to be able to understand. So it's very important, right? And here we'll be talking about things like ultrasound, and I think you need to understand what we mean by ultrasound. It means an ultrasound is the sound that has a frequency that cannot be heard by a human ear. So this is what we'll be talking about in terms of Doppler's effect. I believe that, if I'm not mistaken, the frequency that a human ear can hear, I think it was around 20 20 kilohertz, if I'm not mistaken. So which means any frequency that is above 20 kilohertz, it's actually regarded as an ultrasound frequency, but it's just the frequency that cannot be heard by a human ear. Right. Then now, without wasting time, ladies and gentlemen, I want us to take you through what I just explained now. Then the last one, which I forgot to edit, is the part of the light, where we'll be talking about the red and blue shift, how light explain the difference between red shift and blue, I'm to say blue shift, I apologize. So we'll be talking about this in terms of light. Now, without wasting time, ladies and gentlemen, let me now explain all the components that I just said now. So we're now able to define what is Doppler's effect, which is the apparent change in frequency of the sound detected by the listener, because the sound source and the listener have different velocity relative to their to the medium of sound propagation. So that is what you need to be able to understand. And again, in terms of explaining the change in pitch or the change in frequency were observed when the source moves away or when the source is moving towards the listener. So these are the things that you need to be able to understand when you are dealing with Doppler's effect. Right, without wasting time, let me now take you through what I just said now. Now, in terms of what we just said, number one, we defined what is Doppler's effect. I believe you are sorted in terms of the definition. So now I want us to look at the relationship between the frequency and the wavelength of either in sound or in light. Right, let me take you through grade 10. You recall that in grade 10, when we are talking about waves, when you're talking about the wavelength, let me just, I'm going to say the waves, let me just say wave, not necessarily in terms of the wavelength. Right, when we're dealing with waves in grade 10, you'll realize that if you have, let's say you have something like this, which we can call it a wave. So now on this wave, ladies and gentlemen, even though it's not well drawn, you will realize that the highest point of this wave, it's actually called a crest. The highest point of the wave is called a crest, and the lowest point of the wave is called a trough. So now within these within the wave we're talking about, this wave, we assume that it is traveling at the same speed, which you call it a wave speed, So now this wave speed, we can regard it as the V, the V as the speed of wave, as compared to when we are talking about the speed of light, which is C. So C is the speed of light, and V is the speed of actually, let's say sound waves, let's say the speed of sound waves. So now, if we look at this, on the wave, we have parts of the wave. We know that from one crest to another crest, the distance between two crests or the distance between two trough, we regarded this as the wavelength. This is called a wavelength, the wavelength. So it means the wavelength, it is the maximum distance between two successive crests or two successive troughs. So this is actually the wavelength, which is denoted by lambda. So it means the lambda here, it's regarded as the wavelength, and is regarded as the wavelength, which is measured in meter. It is measured in meter. Then again, remember I said the wavelength is the maximum distance, or the distance between two successive crests or two successive crests. So this is our lambda. We call this lambda. So this is our wavelength, which is measured in meter. Then we also have what is called the frequency. The frequency, it is the number of oscillation, the number of oscillations, the number of oscillations per unit time, the number of oscillations per unit time. So the upwards and the downwards movement of wave that actually determines the frequency. So in other words, this frequency is actually measured in hertz. The frequency is measured in hertz. You'll recall that from grade 10, we used to calculate frequency by using frequency is equals to 1 over period. I mean, this is from grade 10, where we said F equals to 1 over T. So which means if we know the period, we can be able to calculate the frequency from what we have learned in grade 10. So it means frequency is 1 over period. But from this, in relation to the wavelength and the frequency, which is denoted by F, and the speed of sound, there's a formula which says the speed of sound is equal to the product of the frequency and the wavelength. So it means this is the formula for calculating the speed of sound, or the wave speed actually, the wave speed. So this is the wave speed in meters per second. Then this is the F is the frequency, and lambda, it is the wavelength. So now, let us now make frequency the subject of the formula. So to make frequency the subject of the formula, it means we have to divide both sides of the equation by the wavelength. I'm saying, right, this will be V equals to F times lambda. We divide by the wavelength, and we divide by the wavelength. So let's now divide this. That means that frequency will be the speed of sound divided by the wavelength, or the wave speed actually. So now, if we are relating this, guys, I want us to look at the relationship between the frequency and the wavelength, assuming that the wave speed is the same. I want now to compare the relationship between the frequency and the wavelength, assuming that the wave speed is the same. We know that in mathematics or in physics, if you have an equation, let's say you're having y equals to k over x. Any expression that is at the denominator, if we are comparing it with our equation, these are always inversely proportional. In physics, you need to be able to understand what do you mean by inversely proportional. It means if we increase the denominator, this expression will actually decrease, provided this is constant. So they are inversely proportional, which means the higher the x, the smaller the y. And the smaller the x, the higher the y. But when you're comparing the denominators, these are always directly proportional. So now I want us to compare the relationship between the frequency of sound, or actually let me just say the frequency and the wavelength, because it can be of sound or it can be of light. So it means that when we look at this, if we assume that this wave speed, or the V, is constant, then if we want to compare the relationship between the wavelength and the frequency, they will be inversely proportional. So which means the wavelength and the frequency are inversely proportional. They are inversely proportional. What does this mean? It means the longer the wavelength, actually, let me say longer wavelength has shorter frequency or lower frequency. Where if the wavelength is longer wavelength, which is denoted by lambda, implies shorter or lower or shorter frequency. So it means the longer the wavelength, the lower the frequency, and which means that also the lower the pitch, because the pitch and the frequency are directly proportional, which means that if we say the shorter the wavelength, shorter wavelength always imply higher frequency. It means we say they are inversely proportional. They're inversely proportional. The shorter the wavelength, the higher the frequency or the higher the pitch of sound. So it's very important to know the relationship between the frequency and the wavelength. They are inversely proportional, which means an increase in one variable will result in a decrease in the other variable, or a decrease in one variable will result to an increase in the other variable. They are inversely proportional. I believe you are following. You are now following. Then again, you need to understand or to differentiate between the frequency of the listener and the source when the source is approaching the listener or when it is moving away from the listener. So I want us to talk about this because this is very, 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 very important. I will do this by giving examples. I believe you will all enjoy the session. Right, without wasting time, let me now, okay, sorry, I think. Let's now go back to our video again. Right, then now, from here, we went through the relationship between the wavelength and the frequency. We've seen that wavelength and frequency are always inversely proportional. Right, then now, assuming that the wave speed is the same, we assume that the wave that we're talking about is just moving at the constant speed. So which means that the frequency and the wavelength would be this equal. I'm saying they will be inversely proportional. I apologize. Right. Then again, let's now talk about something like this. Let's say you are a person. Like let's say I apologize, guys. Let's say a person is standing next to the road. A person is just standing next to the road. And this person, since is standing, which means the frequency of, or the speed of this person, it's actually 0 because it's just standing. And then now, let's assume as an example, there is a truck or there is an ambulance that is actually moving along the road with its speed or velocity if we are considering the direction. Then now, obvious, what will happen if this is the ambulance and is the one which is producing sound with its siren inserted on it? Obvious, if it's the one that is producing sound, will be regarded as the source. We'll call it a source because it is the one that is producing sound, which means this person will be the listener or the observer. And since he's the listener, what do you think will happen, or what do you think will happen to the frequency heard by the listener? You see, this is the FL represent the frequency heard by the listener. Then the Fs, it is the frequency of the source. So Fs is frequency of the source, Fl is frequency of the listener. Obvious, if the source is moving towards, or it's actually approaching, if the source is approaching the listener, the frequency heard by the listener would not be the same as the source moves away from the listener. So now we want to talk about a case where the source is approaching the listener and it's also moving away from the listener. Same ambulance, moving at the same speed, is just an assumption, moving at the same speed, but now we want to compare the observed frequency. The observer or the listener is one the same thing. So now, what would actually happen if the source approaches the listener and suddenly moves away from the listener? I want you guys to listen to me very well. Obvious, what does this mean? It means that because the ambulance is moving at the constant speed, it means that the frequency produced by the source will still be the same this side. So it means if this one came with a frequency of 400 kilohertz, it will still be the same even if it's moving away. Why? Because they're moving it is moving at a constant speed. It will only change if the speed of the ambulance changes, but we'll talk about that. Now, what does this mean, guys? It means in the examination, you must be able to know the differences where the source is approaching the listener and also when it is moving away from the source. When we talk about approaching, is the same as when we say it is moving towards the listener or it's approaching the listener. So what does this mean? It means that when the source is moving towards the listener will start to hear a higher pitch, or the pitch observed by the listener will increase or will be higher than that of the source because it is now approaching. Why is this the case? It's because as the source is approaching the listener, the wavelength of sound becomes shorter. The wavelength of the sound, when it was still far away, the wavelength it's long. But as it starts to approach, to come closer and closer to what? To the listener, the wavelength becomes shorter. And if the wavelength starts to become shorter, we know the frequency will be higher. So which means that in your calculations, when the source is approaching the listener, always the frequency of the listener or the frequency heard by the listener must always be greater than the frequency of the source. So in your calculation, frequency of the listener must be greater than the frequency of the source when the source is approaching, especially when we talk about approaching. It can be the listener which is approaching the source, or it can be the source that is approaching the listener. But the frequency of the listener should be greater than frequency of the source. Should be greater than frequency of the source. But as the source moves away from the listener, remember when it is exactly closer to the listener, the frequency of the listener and the source will actually be the same. But as the time as it starts to move away from the listener, the frequency of the listener decreases. It decreases. Why? Frequency of the listener, it's now smaller than the frequency of the source. The question is, why are we saying the frequency of the listener initially it was higher than that of the source, but as long as it moves away, the frequency of the listener becomes smaller than the frequency of the source? What could be the possible reason? The reason is that as the source is moving away from the listener, the wavelength, that shorter wavelength start to be longer. The wavelength start to be longer. And we know that the wavelength and the frequency are inversely proportional. The longer the wavelength, the shorter, the lower the frequency. So you need to be able to know the relationship between the frequency of the listener and the frequency of the source as the source is approaching and also as it's moving away from the listener. So in your calculation, ladies and gentlemen, The listener should always be higher than the source if the source is approaching, if there's an approaching or moving towards. But as long as the source is moving away from the listener, the frequency of the listener should decrease or should be less than the frequency of the source. Even when you're doing the calculation, you need to confirm this. All right, without wasting time now, since I have explained the difference, I've differentiated between frequency of the listener and of the source or the observer. When the source is approaching, it's when the source approaches the listener and or when it's moving away from the listener. Now I want us to use the Doppler's equation in calculation. Right, I want to tell you something very important when you are dealing with this Doppler's effect equation. All right, without wasting time, let me write down the Doppler's equation. Right, Doppler's effect equation. According to the Doppler's effect equation, it says, if you want to determine the frequency or you want to look at the apparent change of frequency between the source and the listener, number one, you need to be able to know to actually understand or to know the speed of sound in order to determine the apparent change in frequency. So according to the formula, it says FL, and you must listen to me, FL equals to Fs into V plus or minus VL over V plus or minus VL. So, I'm saying VS, and I apologize, VS. And what does this mean, guys? It means that if you are dealing with, we want to do calculation in Doppler, you can either use the plus formula or the minus formula. You can use the plus formula or the minus formula. However, you cannot use them both, you have to choose one. So I want to explain something here. Remember I said the FL here, it is the frequency, of the listener. We know frequencies measured in hertz, and the Fs, it is the frequency of a source or the producer, which is also measured in hertz. The V here, it is the speed of sound. The speed of sound, usually it's 340 meters per second. But if they don't give you if they don't tell you this, it means they will give you the speed of sound, except that. Then we have VL, which is the speed of the listener. This is the speed of the listener if we are not considering the direction. But if you are considering the direction, it will be the velocity. Then you also have VS. This is also the speed of the source. The speed of the source. So now I want you guys to listen to me very well. Here, when you are dealing with Doppler's effect equation, either you use a plus formula or you use a minus formula. But I want you guys to listen to me very well. Right, in this session, I will always use the plus formula. I want us to use the plus formula instead of the minus formula. But if you want to use the minus formula, still there's no problem. So I want to explain why I want us to use minus formula. I'm saying plus formula. If you are using a plus formula, the one with the plus, then this is what you need to consider when you are dealing with Doppler's effect. Number one, I apologize. If we have a source, you must listen to me very well. Let's say this is our source, and this one is the listener. So I want to talk about a case where the source is approaching or it's moving towards, and also when it is moving away. I want you guys to listen to me. Listen to me very well. If we are using the plus formula, it means, remember this is the source, it means this will have Vs, it will be Vs, and this one will be VL. I want you guys to listen to me very well. If we are using the plus formula, in order to increase the frequency of the listener, it means the denominator should decrease. If the denominator decreases, then this will become higher. So how are we going to decrease this? It means now, listen to me very well. When the source is approaching the listener all the time, if the source is approaching the listener, always, if you want to use a plus formula, velocity of the source should be negative, and the velocity of the listener should be positive. So it means you take the velocity of the source as negative and the velocity of the listener as positive. But immediately when the source moves away, still using that formula, you change the signs. If the speed of source is negative, now it will become positive when it is moving away. But if it was still approaching, Vs becomes negative, away Vs becomes positive. So it means you must always know that, okay, if I'm using a plus formula, the Vs should be negative, then away the Vs should be positive. So that it means that if the frequency of the source is negative, then it means that this negative, when you substitute in the plus formula, the denominator, the speed of sound will decrease by the speed of the source. So, and if the denominator becomes smaller, it means the frequency of the listener will be higher. Okay, I apologize, just a minute. So now, but if you want to use a minus formula, it means you must do the opposite of what I said. So to avoid any complication, let's always use a plus formula. So it means in this paper, I want us to use the plus formula. But if you want to use the minus formula, still there is no problem. I believe you are following. Just a minute, guys. Okay, so it means now, because I said we are going to be using a plus formula, then when we use a plus formula, ladies and gentlemen, always you do this. If the source approach, once they say the source is moving towards, or they talk about towards, you must take the Vs to be negative. And if it's moving away, you change the sign, it's now positive. So it means if Vs is negative, Vl will be positive. If Vs is positive, Vl will be negative. So you always interchange the sign, but by using a plus formula, By doing this, it means that by so doing, it means always if the source is approaching the listener, the frequency of the source will be higher than the frequency of the listener. I'm saying frequency of the listener will be higher than the frequency of the source. But immediately it moves away, frequency of the listener will be less than the frequency of the source when you're using a plus formula, but you can still use a minus formula. So it means here, when we are going to do the calculation, if it's approaching, this will be positive, this will be negative. Moving away, plus, minus. Then you just interchange the sign. But don't forget, Vs approaching is negative, Vs away, it's positive. So Vs negative, Vs positive. Vs negative, Vs positive. Okay, just a minute. I was on a call. All right. So as I was saying, all of the time, you consider the signs, listen, but you can use the plus. But to be on the safe side, let's use the plus. To know that when you are using a plus, when the source approach, Vs become negative, moving away positive. You just look at the Vs, you know if it's negative for Vs, VL will be positive. Away, if Vs is positive, VL will be negative. That is what you need to know when you are dealing with the Doppler effect equation. Very important. We choose to use a plus formula. Then if you want to use a minus, it's still fine. There's no problem. But you need to do the opposite of what I just said now. Right. Without wasting time, guys, without going through the examples, I want us to look at, okay, let me first talk about the applications of Doppler's effect. Then after the application of Doppler's effect, we'll talk about the difference between red and blue shift. And due to time, I'll just take you through 2 examples of Doppler's effect in terms of calculations. Then I will leave you with 1 question where you'll do it. Then wherever you do not understand, then you reach out to me. I'll be available to assist you. Right. Now, we went through the Doppler's effect for formula. Then now I want us to look at the application of Doppler's effect, particularly in medicine. Let's now talk about the application of Doppler's effect, particularly in medicine. Guys, these are exam typical questions. You need to be able to know the application of Doppler's effect. Right, in medicine. Right, in medicine, there are 2 machines, or there are 2 components that they actually use this Doppler's effect. Number 1, it's what you call a Doppler flow meter. Doppler flow meter. The Doppler flow meter, and what you call ultrasound scan. Ultrasound scan or machine. In other book, they call it a machine. Right, these are the 2 components that actually uses Doppler's effect in medicine. Right, what is this Doppler's flow meter and what is its function? A Doppler's flow meter in medicine, it is used to measure, the blood flow rate, particularly in humans, but not necessarily in humans only, but it's just an instrument that is used to measure the blood flow rate. How fast is the blood running? So, or actually it can be used to measure the heartbeat. Also, it can be used to measure the heartbeat in a fetus or on an unborn baby. So this is one of the apparatus used in medicine. And we also have another one which is called the ultrasound machine. Right, the ultrasound machine is just used to check, actually they use to check the status. It's usually used to check the status of a fetus, the status of a fetus or unborn baby in a pregnant woman. So it's very important to know that. So it is used to check the status of the fetus actually, or the unborn baby in a pregnant woman. Usually if they want to check like the status of like the way he's positioned, and also to look at actually, let me just say general cases where they want to check whether it's a boy or a girl or those kind of things, then they actually use ultrasound machine to check the status of the fetus or unborn baby in a pregnant woman. But in the law enforcement, or the traffic officers, in the law enforcement, traffic officers, they usually use what you call a radar scan or a radar gun. So I'll say traffic officers or the traffic police officers or police, they use what is called radar gun. They use something called a radar gun, especially on roads, to detect the speed, or actually to measure the speed of coming vehicle. So this is very, very, very important when you are dealing with Doppler's effect. Okay, guys, I apologize. Just okay, guys, I apologize. All right, welcome back again. I was talking about the law enforcement or the traffic police, how they actually use this Doppler's effect process. They actually used what is called the radar gun to detect the speed of an oncoming vehicle. So you need to be able to know in the exam that once they say mention one application of Doppler's effect in medicine, that means you either talk about Doppler flow meter or the ultrasound machine. But if they did not specify whether in medicine or in law enforcement, you just mentioned any. Then another thing, it is the issue of the red shift and the blue shift, particularly when you are talking about light. Right, you'll recall that from grade 10, if you recall, we have what you call the colors of spectrum, which is called the Roig beef. Let me talk about them. Roig beef. Roig beef, which represent R, it's red, O, it's orange, then Y, it's yellow, this is green, and this is blue. Then we have indigo, and lastly, we have violet. Right, in terms of the colors of spectrum, the red, it is the one with the shortest wavelength. I'm saying the longer, apologize. The red is the one with longer wavelength. Red color has longer wavelength. So now I want to talk about the red shift and blue shift. Red light has longer wavelength. While now, since I'm comparing red and blue, it means as you move towards the violet is the one with the shortest wavelength, the one with the shortest wavelength. And we know, according to what I said, that the higher the frequency, the shorter the wavelength. So if we are comparing red shift and blue shift, I'm saying blue color, I apologize. Blue color has shorter wavelength as compared to what? Shorter wavelength. And we know that a light that has shorter wavelength, it means its frequency will be higher, which means that when we are comparing, and guys, this is also important in the photoelectric effect. When we are comparing the red light and the blue light, red light has lower frequency or shorter frequency. So what does this mean? That if we are talking about the red shift and the blue shift, right? If we are comparing this in terms of the Earth, if the light, or in terms of the Earth, let me just, so we want to relate we want to talk about the issue of light. We want to apply Doppler's effect in the issue of light, or how the red shift or the blue shift occur when observed from Earth, right? I want you guys to listen to me very well. If, let's say, we are on Earth, or this is the Earth. Now, I want you guys to understand something. If this is the Earth, and let's say we have a light. Let's say this is a light. And if, for example, if this light tend to move towards Earth, if the light tend to move towards Earth, and also the light is moving away from Earth. I want you guys to away from Earth. So it means that in the context of what we just said now, if the light is moving towards the Earth, it means if we are comparing this, we are saying that it is moving towards the Earth because it has a shorter wavelength. And guys, I want you guys to listen to me. Since it has a shorter wavelength because it's approaching the Earth, it means it's the one that has higher frequency. It is the one that has a higher frequency. So now, but if the light is moving away from the Earth, then, or actually, let's not talk about light. Let's just talk about stars in essence. Yes, let's talk about the stars. So if the stars are observed to be moving towards the Earth, it means they are moving towards the Earth because there is a shorter wavelength. And if there's a decrease in wavelength, it means the frequency becomes higher. But if the stars are seen to be moving away from the Earth, it means they're moving away from the Earth because they are having a longer wavelength. They're having a longer wavelength. And since they have a longer wavelength, it means they have a lower frequency. Now, I want us to compare this with what you call a red shift, red and blue. All right, you see that if there is a longer wavelength, frequency becomes lower. And what does this mean? It means this has to do with red light, because a red light is the one that has longer wavelength and lower frequency. So what does it mean? It means if the stars, when the stars are moving away from the Earth, this has to do with what you call a red shift. Why a red shift? If they're moving away from the Earth, they tend to have longer wavelength. And since they have longer wavelength, the frequency becomes lower. So it means this is called a red shift, because a red color, we know, is the one that has longer wavelength but shorter or lower frequency as compared to blue. So it means if the stars are moving towards the Earth, if the stars are moving towards the Earth, it means they are moving towards where there is a shorter wavelength, and it means the frequency is higher. It means this is called a blue shift. So what does this mean? Blue shift occurs when the stars moves towards the Earth, and red shift occurs when the stars are moving away from the Earth. And when the stars are moving towards the Earth, it means they're moving towards the sides where there is a higher frequency. The frequency tends to be higher with a shorter wavelength. But as long as there is a longer frequency, it's a longer wavelength with low frequency, it means that the stars are moving away from Earth. And this is called a red shift. I believe you understand what I just said. Now, let's now deep dive into the examples, taking into account what I just said. Now, without wasting time now, ladies and gentlemen, let me go through one question. Then I will also create another video to finish other activities. Due to time, guys, due to time, I'll not be able to go through all the sessions, but I believe you will enjoy what I'm going to do now. So I'll just do one example, then the others I'll just go through them, but you must make sure that you try to solve them on your own. So I'll just talk about this, then after this one, then we'll end the session. But also you can go through these on your own. A patrol car is moving at a constant speed, but I'll also create another video just to address this. Yeah, just to address this due to time, guys. Due to time, stage 2 application of Doppler's effect. You see, they did not specify whether you're talking about law enforcement or medicine, so you can state any. Right, this is another case where they say ambulance is traveling towards the hospital at a constant speed. And we know in physics, when they say constant speed, what does it mean? It means the acceleration is zero. Final and the initial are equal. So it's very important. So yeah, just without wasting time, let me just go through the first question, ladies and gentlemen, to address what I just said now. Then the rest shall follow. Right, let us now go through the question without wasting time. I apologize, guys. Okay, here it's a question. It says a police car is moving at constant velocity on a freeway. Ladies and gentlemen, this is a question. A police car is moving at a constant velocity. At a constant velocity, we know constant velocity or constant speed, it means the acceleration is zero acceleration. This is a police car, it's moving at a constant speed or velocity for the direction on a freeway, So let's assume this is a freeway. Then now we have a police car. Here it's a police car. We need to be able to know, is this police car the source or the listener? The siren of the car, okay? The siren of this police car emits sound waves with frequency of 330. So it means this is the source. It means this police car is the source because it's the one with the siren on it, which means we are given the frequency of the source. Okay, let me just try to draw it here so that you can see it nicely. Right, so it means this is the source because it's the one that is emitting sound waves from its siren. So it means this is the police car, and this police car is regarded as the source. This is the one that is producing sound. So it means we need to know the velocity of that source. Right, we know the frequency of the source. The source is producing a sound of 330 hertz. Right, even if I do not go through this, then they said a stationary sound detector, which means this is the listener, a stationary sound detector. So it means along the way, there is a listener here. There is a listener, and this listener, it's not moving. So it means its speed or the velocity, it's zero. Why are we saying zero? Because they're saying it is stationary. Right, now look at these guys. We need to understand something. We know that if the source is moving towards the listener, frequency of this listener must be bigger than frequency of the source if we are talking about approaching or moving towards. But if it's moving away, the frequency of the listener should be less than the frequency of the source. So you need to understand that. But now look at this. They're saying a stationary sound detector measured the frequency of the sound waves of the approaching siren. It measured the frequency of the sound waves emitted from the siren as or sound wave of the approaching, or when this was approaching. We are told that when the source is approaching the listener, frequency of the listener or frequency heard by the listener became 365 hertz. You see, it's true because you see that frequency of the listener is higher than 330. 365 is higher than 30. So it shows that this is the case where the source is approaching the listener. And what did I say? I said, when you are using a plus formula, ladies and gentlemen, Vs should be negative and VL should be positive when we are dealing with approaching. But when you're moving away, you change the sign. Vs becomes positive, and VL becomes negative. Don't forget that. Right. Then now they're saying take the speed of sound in air to be 330. So we're given V. The V is 340 meters per second. So it's very, very important. Okay, right. Now, Without wasting time, the first question says, state Doppler's effect in weights. I believe you can do that. Then here it says, calculate the speed of the car. We want to know what is the speed of the car here. Already they're saying this car, police car is traveling at a constant speed. So it means the speed will be the same all over. So it means to do that, we're gonna use a plus formula to say FL equals to Fs into V plus VL over V plus Vs. And what did I say? Let's check what we're given. We're given the information when the source is approaching the listener. So it means now we have to use the option of making Vs to be negative and VL to be positive. So it means the formula will be Vs, I'm saying VL, I apologize. VL equals to, I'm saying FL, it's equals to Fs into V plus VL over V minus Vs. So now this why are we using this is because we are talking about the case where the source is approaching. It means Vs should be negative, VL positive, but moving away, we change the sign for a plus formula. Let's now substitute. What is the frequency of the listener? It's 365. Frequency of the source is 330 into 340 plus. What is the frequency of the listener? 0 divided by speed of sound, 340 minus Vs. We want to know the speed of the car. Then now to do that, let's now, okay, we know this is the same as, let me take it here. This will be 365 equals to 330 into 340 plus 0 is 340 divided by 340 minus Vs. So since this is a fraction, we can make this one over 1. Then let's now multiply. This will be 365 equals to 330 multiplied by 340. 330 multiplied by 340. So this will give us a value of 11200. Then we multiply the denominator. 1 multiplied by 340 minus Vs. This becomes 340 minus Vs. Then we make this one over 1. We cross multiply. Cross multiplying, this would give us S equals to 112200. Then we can either remove the brackets or we divide everything by 365. Let's divide by 365 here. So this will give us 340 minus Vs equals to then 112200 divided by 365. So this will give us a value of 307.40. Then let's make Vs the subject. So it means Vs will be 340 minus 307.40. So it means Vs will be minus 340. So this will be 32.60, if I'm not mistaken. Let me just confirm. 340 minus 307.40. So this will give us 36.60 meters per second. So it means this was traveling at the speed of 36.60 meters per second. So 330 into 340 divided by 340 minus 32.60. So that will give us roughly 365. So it means even if we do the calculation where the source is moving away, the frequency of the listener should be less than the frequency of the source. Then lastly, it says the spectrum of a distant star when viewed from an observatory on Earth, it appears to have undergone a redshift. So use the knowledge of the Doppler's effect to explain the term redshift. Then you are going to say when the stars moves away from the Earth, okay, then it means there is a decrease, or yes, due to the decrease in, this is an indication that we have a longer wavelength. The wavelength becomes longer. And if the wavelength becomes, I'm going to say, yes, no, the wavelength becomes longer, it means we have a lower frequency. So it means a redshift actually occur when the stars are moving away from the Earth. So when the stars are moving away from the Earth, it means there is a decrease in wavelength, which results to a lower frequency. So it means the stars are moving towards the Earth. It means now, I'm saying away from the Earth, where there is a longer wavelength and a shorter frequency. And this is actually called a redshift. So I believe you understand, guys. Then I'll continue with the other parts of this video, particularly in the next video. But I believe you enjoy the session. Okay, thank you very much for listening. I apologize for technical issues. See you the next session. Thank you very much. Bye-bye.